Hey guys, today is the second day of lesson 714, and it's going to be focused around finding coordinates on the unit circle, which we'll get into in a little bit. But first I want to do this little warm-up with you just so we can refresh ourselves with special right triangles. So, for this first one, hopefully you can tell pretty quickly that it's a 30, 60, 90, and we know that because of this 30 and this 90. There's nothing else it could be. So we use the little prototype triangle to determine what the sides are. If you guys remember, it's kind of ugly, sorry. We know that the hypotenuse is going to be 2 times the shortest side. Right, our shortest side, we'll call it x, so our hypotenuse will be 2x, and then the medium side is going to be that short side times the square root of 3. Alright, so now, that in mind, we want to go ahead and match the sides on this triangle to the sides on our model triangle. So we know that the information that we have right here is the shortest side because it's across from the smallest angle, the 30 degree. So 4 is going to be x. Right? So now that we know that 4 is x, we can pretty easily find b because we know that b is going to match with the 2x side. Alright, and that being said, we can finally deduce that a matches with our x root 3 side. Okay, so now that we know that 4 is x, we can find b by doing 2 times it. So let's do another color here. So b equals 2 times x, which in our case is going to be 2 times 4. So it's going to be 8. And then for a, we know that a is equal to x times the square root of 3. And so that's going to be 4 times the square root of 3. Alright, and that's it. We have found all the missing sides to our triangle. So that's how we do the 30, 60, 90. Let's go ahead and do a 45, 45, 90 now. Let's draw the model triangle first. Yikes. Slightly better, maybe. Okay, so our 45, 45, 90, we know that the legs are the same. Those are going to be some x. And then the hypotenuse is the value of x times the square root of 2. So we've been given the side that is the leg, which is nice. It makes it easy on us. So if this leg is 5, we can say that this leg is also 5, because again, we know that the 2 legs are going to be the same. So we know that a is equal to 5. And b is equal to x root 2. Right? This one's x, this one's x. So b is going to be 5 root 2. And that's it. So we'll kind of change gears for a second, and then we will go back to why this was relevant. Alright, so to start talking about the coordinates, we've been talking about spots on the unit circle and figuring out both horizontal distances from the spot on the circle, like the position and the ride, to the y-axis. That was our horizontal distance. We used cosine for that. And then for the vertical distance off the ground, we used sine. So if you kind of imagine a point on a graph, right? Let's say we had some random point like this one right over here. We know that the horizontal distance is going to be the x-coordinate and the vertical distance is going to be the y-coordinate. So the coordinates of this point are 3, 4. Alright, because the 3 is the horizontal distance and the 4 is the vertical. You guys all know how to do that. Now I want you to imagine kind of a graph on the unit circle, and that's why we have axes here, right? It is basically a graph on the circle. So let's say that we have some kind of spot on the unit circle, and we are making an angle out of it. So this is some theta. Remember, that's our Greek letter for an angle. Then the coordinates of this, we have to think about, again, the horizontal distance for the x and the vertical distance for the y. And we've already talked about how the horizontal distance is always going to be dependent upon cosine. So we know that in order to find the x-coordinate, it's the cosine of whatever your angle is. And sure enough, you might be able to guess this next one. Your vertical distance off the ground, your y-coordinate, is going to be sine, because we've always used sine to find the height of any spot on the unit circle. So your y-coordinate is going to be sine. All right, so just like how you have an xy coordinate on a regular graph, you'll have an xy coordinate for the unit circle too, but we're just going to be using cosine and sine to find those. All right, so let's go ahead and practice and just see what this looks like in a very basic situation. If I wanted to find the xy coordinates of an angle that's 135 degrees, or like at the 135 degree position on the unit circle, you literally just need to take the cosine and you need to take the sine. So we would do cosine of 135 and then comma sine of 135. So in your calculator, if you type in cosine of 135, that gives us negative 0.71, and if you do sine of 135, you would get 0.71. So our coordinates for this are going to be, negative 0.71 and 0.71. Just be sure not to mix up the cosine and sine. It's very important that cosine, you remember, is x and sine is y. So for the next one, for 330, we'll do the same thing. You do cosine of 330 and sine of 330. So if you type cosine of 330 in your calculator, you would get 0.87. And if you type sine of 330 in your calculator, you get negative 0.5. So those are my coordinates. And that's all there is to that. So now, those are decimal coordinates, which are nice and all, but there are some particular areas on the unit circle where we can find exact coordinates, and those are going to be the ones that we're actually the most interested in. So we can do that by using special right triangle properties, which is why we did a warm-up on that. So let's start with a 30-degree angle. If we are at the 30-degree position on our screamer ride, or the unit circle, we can know right away that we're going to be using a 30, 60, 90 triangle. So let's go ahead and draw our little height down here to help us make the triangle. Right here we have our triangle, so let's go ahead and draw a bigger version of that. I'm going to go ahead and try to cheat here so that it doesn't come out hideous. Oh, nope, that's not the kind of line I wanted. Okay. So we've got our sides. Okay, so we know that the angle here is 30, and we know that the hypotenuse is 1. We always operate like that. Now, based on our model 30, 60, 90 triangle, which we could just draw here, this is not a very good 30, 60, 90. Honestly, it kind of looks like a 45, 45, 90, but it's fine. You guys get the point. So these are my 3 sides. Maybe we can do this to be more clear. Okay. So we can say right away that the longest side right here is 1, and it's going to match with our 2x side on the model triangle. So we know that 1 is going to equal 2x. So let's go ahead and solve for x by dividing by 2 on both sides. The 2's are going to cancel, so we find out that x is equal to 1/2. So we know that this right here is going to be 1/2. And then because this side is x root 3, it's basically going to be 1/2 times root 3. So x root 3 is going to be 1/2 times root 3. Now, when you multiply something by itself, like something that's not a fraction, by a fraction, it goes to the top of the fraction by default. Like it multiplies by the top. So another way you could just write this is root 3 over 2. All right, so this tells us that the, let me write that right here. This tells us that the horizontal, like the base of this triangle, is root 3 over 2. That's a slash, this is a fraction. Maybe I should write it the other way. Root 3 over 2. And this side right here is 1/2. So that right there gives us the coordinates. This is the horizontal, so the x, this is the vertical, so the y. So my coordinates in exact form. Exact means not with decimals. It's root 3 over 2 and 1/2. All right, and that's it for that triangle. So let's go ahead and take a look at the very last one here. This 60-degree angle, I want to do it next for a reason that's going to become pretty apparent in a second here. So let's draw down the height. Here's our triangle. So let's once again create that triangle over here. All right. So here's our 30, 60, 90 triangle. And hopefully you guys remember that the one we did up here was also a 30, 60, 90 triangle. So let's see if we notice anything interesting. We know that the hypotenuse is going to be 1. This is the 60-degree angle. This is the 30-degree angle. So if we were to draw our model again, I like to just draw the model in the same orientation of the triangle that I'm working with. It just, I feel like, makes lives easier. 2x, x, x root 3. You notice that we're starting with the same information. In the first 30, 60, 90 triangle we did for the 30 degree, we started with a hypotenuse being 1, and we found our other two sides. And this one, you'll notice hopefully that it's just a rotated version of that triangle we worked with before. So the pieces are going to actually be pretty much the same, because if you actually start doing the work, so we know 1 is the 2x, we solve for x, we get x is 1/2 again. It's just a question of which side matches with who. So this time our 1/2 belongs on the base as opposed to the height. Like over here was the height. And then sure enough, my height this time is going to be root 3 over 2, just like we had for the other one here. So we really didn't have to do a lot of work for this one because we honestly already did the work before. So this time, kind of just flip-flopped. We know that there's a 1/2 down here for this length. And for this one, it's going to be the root 3 over 2. So the coordinates are the same as the other ones, just flipped. The 1/2 is the x because it's horizontal, and then root 3 over 2 is the y. All right, so let's go to our final one here. It's a 45, 45, 90 because we're at a 45-degree angle here, and I'm kind of running out of recording time, so I'm going to do a little prep work for a second while I pause it. Okay, so we can see that the hypotenuse here will match with the hypotenuse here, so I set 1 equal to x root 2 and solved for x by root 2, and so these cancel, and so basically x equals 1 over root 2, but because in math we typically don't like to have square roots on the denominator, I'm going to do something called rationalizing the denominator, which essentially just means I'm multiplying the top and bottom by root 2, so it gets rid of the square root. So ultimately we end up with root 2 over 2. So that's going to be these two sides right here, And in turn, it's going to be my cosine and my sine. So my coordinates are root 2 over 2, comma root 2 over